A telescope is an instrument that allows us to observe distant objects by collecting and focusing light. Telescopes have been vital in expanding our understanding of the universe, enabling us to see celestial bodies far beyond the reach of the naked eye, including distant galaxies, stars, planets, and nebulae. There are different types of telescopes: optical telescopes, which use visible light, and non-optical telescopes, which detect radio waves, X-rays, and other electromagnetic radiation. This guide will focus on optical telescopes, which use lenses or mirrors to gather and focus light, allowing us to observe distant objects like galaxies. To understand how a telescope works, it's essential to break down its key components. 1. Objective, primary lens or mirror. The objective is the main part of the telescope that collects light. Refracting telescopes use lenses to bend, refract light, while reflecting telescopes use mirrors to bounce, reflect light. The objective size, called aperture, is critical because the larger the aperture, the more light the telescope can collect, which is necessary for seeing faint and distant objects like galaxies. 2. Eyepiece. The eyepiece is where you look through to see the magnified image. It takes the light collected and focused by the objective and magnifies it further. It doesn't change the amount of light, but it enlarges the image, allowing you to see more detail. 3. Focusing mechanism. Telescopes have a focusing knob or mechanism that adjusts the distance between the lenses/mirrors to bring objects into sharp focus. 4. Mount and tripod. A stable mount is essential to keep the telescope pointed at a distant object without any shaking. When observing galaxies, which appear very faint and small, even slight vibrations can disrupt the view. The primary purpose of a telescope is to collect as much light as possible. Distant galaxies are extremely faint because they are so far away. The human eye doesn't have the capability to gather enough light to see them clearly, so telescopes step in to amplify the amount of light we can detect. Light gathering power. The larger the objective lens or mirror, the more light it can gather. This is why modern professional telescopes, like the Hubble Space Telescope, have massive mirrors. Hubble's primary mirror is 2.4 meters, 7.9 feet in diameter. When light enters the telescope, it hits the objective, which focuses all the light rays onto a single point. The telescope collects light over its entire surface area, which is much larger than the human eye can. How faint objects become visible. Distant galaxies emit light that has traveled millions or even billions of years across space. By gathering as much light as possible, telescopes make these faint objects visible. Essentially, they take in more light than our eyes could ever manage, making distant objects appear brighter and clearer. Once light is gathered and focused, the next critical function of a telescope is to magnify the image, allowing us to see more detail. Magnification. Magnification is determined by the ratio between the focal lengths of the objective lens/mirror and the eyepiece. While magnification is important, it's not everything. You need enough light and resolution for clear images. A high magnification without sufficient light can result in a blurry image. Focal length is the distance between the objective and the point where the light converges focuses. A longer focal length results in a larger image. Resolution. Resolution is the ability to distinguish between two closely spaced objects. It's what allows us to see fine details in the images of galaxies or stars. The resolution of a telescope depends on the size of its aperture. The larger the aperture, the better the resolution. Resolution also depends on atmospheric conditions for ground-based telescopes, which is why space telescopes like Hubble are positioned above Earth's atmosphere, avoiding distortions caused by air turbulence. 1. Refracting telescopes. These use lenses to gather and focus light. The first telescopes used by Galileo were refractors. The objective lens bends the light to bring it into focus. One downside of refracting telescopes is chromatic aberration, where different colors of light are bent by different amounts, causing slight blurring or color fringing around objects. This is less of an issue with modern designs, but it was a problem for early telescopes. 2. Reflecting telescopes. Instead of lenses, reflecting telescopes use mirrors to gather and focus light. These telescopes are more popular for large observatories because it's easier and cheaper to make large mirrors than large lenses. Isaac Newton developed the first reflecting telescope, which solved the problem of chromatic aberration. The largest telescopes in the world, such as the James Webb Space Telescope and the Keck Observatory in Hawaii, are reflectors. When it comes to viewing galaxies, particularly distant ones, there are specific challenges a telescope must overcome. Faint light and exposure time. Distant galaxies are faint because they are so far away. To capture images of these galaxies, telescopes often need to focus on one area of the sky for an extended period, sometimes hours or even days, to gather enough light. For example, the Hubble Deep Field Image, which shows some of the most distant galaxies ever seen, was created by pointing the Hubble Space Telescope at a seemingly empty patch of sky for 10 days, capturing faint light that had been traveling for billions of years. Atmospheric distortion. On Earth, our atmosphere can distort incoming light, making stars and galaxies appear to twinkle or blur. This is why space telescopes like Hubble are so valuable. They avoid the atmosphere altogether, providing much clearer images. For ground-based telescopes, adaptive optics are used. These systems adjust the mirrors in real time to compensate for the distortions caused by the atmosphere, improving image clarity. Wavelengths beyond visible light. Some distant galaxies emit light in wavelengths outside the visible spectrum, such as infrared or ultraviolet. To observe these galaxies, astronomers use non-optical telescopes, like infrared telescopes, e.g., James Webb, or radio telescopes, e.g., ALMA. These wavelengths can reveal details invisible to optical telescopes, such as hidden star formation in dusty regions of space. Hubble Space Telescope. Launched in 1990, Hubble has revolutionized our understanding of distant galaxies. It has taken some of the most detailed images of galaxies, nebulae, and other celestial objects. Hubble's position outside Earth's atmosphere allows it to take clear images without distortion. James Webb Space Telescope JWST. Launched in 2021. JWST is designed to observe the universe in the infrared spectrum, allowing it to see through dust clouds and look farther back in time than Hubble, to the formation of the first galaxies. Keck Observatory. Located in Hawaii, the twin Keck telescopes are the largest optical/infrared telescopes in the world. They use adaptive optics to correct for atmospheric distortion, providing clear images of distant galaxies from Earth. Telescopes work by collecting and focusing light, allowing us to see distant galaxies that are otherwise invisible to the naked eye. Whether they use lenses or mirrors, the primary goal is to gather as much light as possible, magnify the image, and resolve fine details. The ability to peer into the depths of space with telescopes has given us invaluable insights into the formation of galaxies, the structure of the universe, and even the possibility of distant planets that may harbor life. As technology continues to evolve, we'll be able to see even farther and in greater detail, opening up new horizons for our understanding of the cosmos.